Good morning, students. Today I am going to discuss about causes for deviation from ideal behavior. In order to explain the deviation from the ideal behavior, it is necessary to modify the kinetic gases theory of gases. The following postulates of the kinetic theory do not appear to hold under these all conditions. Therefore, to make that is a postulates, that is a few postulates are there, that is a kinetic energy, and that can be modified, then only it gives that is the causes of deviation from the ideal gas, real gases from ideal behavior. The first postulate goes to the postulate number 1. The volume occupied by the molecules themselves is negligible small as compared to total volume occupied by the gas. Therefore, here you have to see that is the total volume of the molecules occupied is negligible because that is so small compared to the total volume of the occupied gas. This can be made by that is a postulate 1 of that is kinetic theory of gases. This can be modified. This postulate can be justified under the ordinary conditions of the temperature and pressure. It can be shown by calculation that some of the common gases means nitrogen gas, oxygen gas, hydrogen gas, helium gas, these are the volume occupied by the molecule themselves under the ordinary conditions is only about that is 0.14% of the total volume of the gas. This is the negligible fraction indeed, but if the pressure becomes too high, say about that is a 100 atmospheric pressure or more than 100 atmospheric pressure, then total volume of the gas decreases appreciably, whereas the volume of the molecules will remains almost the same because the molecules are incompressible. Because when molecules are incompressible, then the volume will be a greater. Hence, under these conditions of high pressure, the volume occupied by the gas molecules will not be no longer to be negligible in comparison with the total volume of the gas. Therefore, this can be modified at high pressure. This is at ordinary temperature and pressure. We say that according to kinetic theory of gases, the volume occupied by the molecules are negligible compared to that is the total volume of the gas. This says that is a postulate number 1 of that is the kinetic theory of gas. But as the temperature increases and as the pressure increases, the volume of the occupied cannot be negligible because it is incompressible and they cannot be negligible, and this can be modified. Therefore, the same things happen when the temperature is lowered far to extent. Suppose high temperature, high pressure, the volume cannot be negligible. It should be considerable. As also we say that is as the temperature lowered to large extent, the total volume of the gas decreases considerably, no doubt, but the volume occupied the molecule themselves remains that is practically the same. In this case, the volume occupied by the molecules will not be no longer be negligible. The postulate number 1 therefore not valid at high pressure and low temperature. Therefore, why the deviation of that is real gases from ideal behavior? Real gases means the PV is equal to nRT. We say that is Z is equal to PV divided by nRT. No, that we have written. For 1 mole gas, that is Z is equal to, that is a compressibility factor. No, and that can be represented when the all real gases should be according to kinetic theory, it will be remains that is negligible, but at high pressure and low temperature, the volume of the gases cannot be negligible. This can be main causes of that is a deviation. At under high pressure and low temperature, the gases cannot be behaved as ideal. And therefore, they deviate from that is the ideal gas equation. This is the first postulate that is the main causes of that is a deviation. Second one is postulate number 2. The forces of attraction between gas molecules are negligible. According to that is the kinetic theory of gases, the postulate number 2 said that the forces of attraction between the gases molecules are negligible. Force will be there, no? The intermolecular forces will be there, that can be negligible. This is assumption is valued at very low pressure. Very low pressure means when pressure will be low, then molecules are very apart, that is they are far apart from each other, and they do not having a attractive force between them. Or high temperature, we say that high temperature also the molecules are gone from, or they are placed apart from each other, and therefore we say that at low pressure and high temperature the attractive force will be almost all, that is negligible. But here we say that is under these the lie apart from that molecule. But high pressure, suppose the pressure converted, that is lower pressure into high pressure, and the high temperature into lower temperature, the volume is small and the molecules lie closer to one another. We say that is high pressure we are taken. After high pressure applying, the all molecules are very very close to each other, and the attractive force exists between that molecules. Also we say that is at lower temperature, when temperature is removed or lowering, the intermolecular, the energy will be less, and therefore all molecules are come closer, and therefore due to a particular distance between them they exist, and hence it get that is the attractive force. Therefore again this postulates the force of attraction between the gas molecules are negligible. This say that is the postulates of that is a kinetic theory of gas, and but that is high pressure and low temperature, this condition will be a reverse. Therefore we cannot be neglect that is the attractive force. There will be some attractive force exist between the molecules, and hence this is the second condition. This you have to modify this second postulate also. We say that the forces of attraction between the molecules are not negligible at high pressure and low temperature. We say that high pressure and low temperature. And this can be second, that is causes are main reason why the real gases are deviate from that is the ideal behavior. Then the third one is van der Waals equation of state. Van der Waals equation of state. Van der Waals proposed his famous equation of state of a real or imperfect gas. He modified the ideal gas equation by suggesting that the gas molecules were not mass points, but they behave like a rigid sphere having a certain diameter, and that there will be exist intermolecular forces of attraction between them. The two corrections terms introduced by the van der Waals described below. Here usually the van der Waals equation he given that is the state of the molecules, and here according to kinetic theory says that the all molecules are molecules having a that is a not point, that is a mass of point charges, but here they having a rigid sphere, that molecule having a rigid sphere, that certain that is a diameter will be there, and attractive forces exist between the molecules are there, and that will be explained, that correction will be made by that is a van der Waals, and that is the first one is nothing but correction due to volume of the gas molecules. Now first correction will be goes to that is what are about that is corrections of that is this will be undergo this also condition under a that is causes of real gases from ideal behavior. The correction due to the volume of the gas molecules. The ideal gas equation, that is PV is equal to nRT, is there. It is derived under the assumptions that that gas molecules are a point masses. The gas molecules having a point masses. They do not have a definite volume. They are considered as these are the assumption made by that is the kinetic theory of gas. molecules are a point masses and they do not having a definite volume. Van der Waals that is further he assumed that and that is modified, suggested that a correlation terms NB, that is N is the number, that is N will be a number of molecules, B is nothing but van der Waals constant, should be subtracted from the total volume of V in order to get that is ideal volume which is compressible. Therefore here the volume correction will be there in the volume equation. No, that certain value will be a subtracted, that will be a term NB value subtracted. Then after subtracting that certain value from that is volume, that molecule is behaves as a compressible and it is ideal. And this can be explained here, that is the volume how it is takes place. I say that is in order to understand the meaning of correction term NB, let us consider the two gas molecules. Impenetrable means the molecules cannot be goes inside each other. They are just compactly or that is closely touching, but they cannot be goes inside the inside from each other. Therefore impenetrable and that is incompressible spheres. Each of has a diameter d. This is the shown in that is the diagram. This is the diagram will be there. This is the diagram. Actually these two molecules are there. This is the one molecule. I say that is this small molecule. Suppose we take that is hydrogen molecule, and this is suppose say that is chlorine molecule. One is bigger, one will be smaller. Here there is these are the two circulars. No, these are the two molecules are not that is a same size, but they are having a differ. Suppose we say that is someone one is that is small means I take as a hydrogen, another one is big as that is a chlorine or bromine, whatever may be. Then here the force will be there. No, the attractive force. This is the internuclear distance. No, this is called as diameter. The centers of the between that is two nuclei of the two molecules. This is the one here, and this is center, and the distance between that is the center of that is this molecule and this molecule. This will be a diameter, that is a molecular diameter will be there. And therefore suppose we say that is this is the, suppose we are the excluding volume of the molecules will be a surrounding here. Now these molecules will be there again, that is a molecular diameter is nothing but we say that is small molecule will be here. Suppose here the last electron will be there, and this is the another electrons, and their distance between this is the molecular diameter of the particular molecule. And here again we say that is a from here and from here last we say that is a molecular diameter of this, but center of the two molecules this is another one will be d, and this is the called as a this area, no, this area covered, this is called as a excluded volume, that will be a here. I can explain here. This is the explain in this diagram. It is evident that the center of the two spheres cannot approach each other more closely than the distance of the d. There, suppose we say that here molecules distance will be there. No, this molecules distance we cannot be approach. Here distance will be fixed here. The d will be fixed. They cannot be here touches. That is the two spheres will be touches each other, but they cannot be further. We cannot be compress. The distance it is will be fixed there, and that cannot be increases. Okay, we cannot be make that is compress, or it cannot, this distance cannot be make that is small or that is again large. Suppose a large we are taken, they cannot be attraction will takes place. Suppose we are getting that is close, the repulsion will takes place, and the distance will be became say that is a fix. For this pair of molecules, therefore the sphere of radius d, and hence the volume of that sphere will be a 4 by 3 pi d3 constitutes what is known as that is a excluded volume. The excluded volume per molecule is the half of that is the above molecule, that is 4 by 3 d of that is 3. The actual volume of the gas molecules radius r is taken as 4 pi by 3 pi r3 4 by 3 pi r cube. This is equal to 4 by 3 pi d by 2, that is r is nothing but the half of the diameter, no, the radius is nothing but distance, half of the distance diameter of that molecule, therefore d by 2, and this is cube, and this will be, after that is simplifying, 1 by 6, that is pi d3 will be there. Therefore the excluded volume per molecule will be nothing but that is 2 by 3 pi d3 equal to, that is a 4 into 1 by 6 pi d cube. This is equal to 4 times of the actual volume of the gas. The excluded volume per mole of the gas would be a, suppose Na is the Avogadro's number, then we are multiplying this will be a, it is getting, that is B. The what is the B is nothing but B is equal to the Avogadro's number into 4 times of, that is a 4 by 3 pi d cube, and where N is nothing but that is Avogadro's number. The compressible volume per mole of the gas would be, that is V minus B. If the volume V of the gas contains a N moles, then the excluded volume will be a NB. Hence the ideally a volume which is compressible would be a V minus NB. NB is nothing but that is a corrected volume, because the total volume will be there, and here that is the NB value, that is the excluded volume, that should be a removed, that should be a subtracted from that is total volume, that given by that is a van der Waals equation. Therefore we say that is here the correction due to the volume of the gas molecules, means simply we say that is the total of the volume of the gas molecules occupied. From that we have to subtract that is a NB value, where B is nothing but that is here Na into 4 into that is a 4 pi by 3, 4 by 3 pi into d cube, and this is the B value, and this is called also called as a van der Waals constant. The volume B per mole as known as that is a co-volume. It is also called as a B is also called as a co-volume. Okay. Now this is the one correction will be made. Then second correction will be there, the correction due to the intermolecular forces for attraction. Intermolecular forces. Now here actually this is the this volume, why it is we are made that is a two correction for explaining that is one is nothing but volume occupied by the molecules negligible, that is that will be a corrected, volume will be corrected, and that will be given by that is a van der Waals equation, by that is how it is corrected, how it is negligible. We cannot be negligible means that should be subtract the total volume of the gas occupied by the molecule. From that the NB volume, that excluded volume, that can be removed, then only we will get that is the actual volume occupied by the gas molecule, and this is the causes of that is ideal behavior, that is ideal behavior of real gases. Then second one is we said that is a forces of attraction. Therefore force of attraction postulate 2, it can be that is proved by that is due to the correction, you are that is given that is a correction due to intermolecular forces of attraction. In the derivation of the real gas equation, it was assumed that there are no intermolecular forces of attraction. Actually it is not so. There will be no intermolecular forces of attraction is that is given by that is a kinetic theory of gas, but there will be attraction will be there. Actually it is not so. In order to take into account the effect of intermolecular forces of attraction, let us consider a molecule lying somewhere in the midst of vessel as shown at the point C here. Here C point. Consider a molecule at the inside by the molecule here C, that is in the figure. As can see it being the attractive force uniformly sideways. There suppose one molecule will be there, and that molecule surrounds the other molecules will be there. The attractive force exists between that is one molecule and other molecules are continuously takes place. Therefore net resulting force will be became a 0. And suppose same molecule will be taken as the surface, where that is here the net attractive force will be became a 0. We say that is the kinetic theory of gas can be explained when the molecule is inside. But same molecule will be present at the that is surface. We say that is this forces molecule here approach at the wall or vessel at the surface. as shown here. W, this is the molecule, it is surface that is present at the surface, W. Then here the attractive force will be exist between this direction, that direction, but opposite direction there is no molecules, therefore there is no force. This molecule undergo a attractive force, therefore attractive force form, that is bulk molecules behind in it. Hence it will be a strike the wall with a lower velocity and the extra lower pressure than would have done if there was no force of attraction. Therefore necessary to add a certain correction factor P. Here there will be pressure will be there. This molecule undergo a pressure, the attractive force will be exist, but here on this molecule there is no attractive force will be there. This molecule holds for, that is a kinetic theory of gas, but this molecule cannot be holds, that is a postulate of kinetic theory of gas. Therefore here this correction P will be a factor will become of the gas in order to a ideal behavior. The correct pressure of, that is we say that is a P plus, that is a P plus P. Therefore total pressure plus, that is a corrected pressure will be there, and this will be a causes for, that is here. Now coming to, that is here, when the pressure is not that is we are saying that is cases when the pressure is not too high, when the pressure is not very high or too high, the volume Vm will be a sufficiently large and B may be ignored in comparison. The van der Waals equation can be for 1 mole gas, it be given, that is a P plus A divided by Vm square into Vm minus, that is B equal to RT. Actually that will be nothing but the actual, that is ideal gas equation is nothing but P plus A divided by V square into V minus B equal to RT will be, that is it is the van der Waals equation. This is called as a van der Waals equation due to it is given, that is modified by van der Waals equation Vm square. Vm is nothing but molar volume, and that can be ignored, that cannot be ignored, and that will be taken, that is account. This will be this equation modify, that is again here. Suppose V minus B, we can say that is B is suppose negligible, then what happen, P into A into V square into Vm is equal to RT, and suppose we are taking, that is multiplying these, we will get, that is PVm plus AVm equal to RT, and this is the Pm equal to RT minus AVm, that is called equation number 2. Thus the product of PVm is less than the RT by an amount of equal to A by Vm, and as the pressure increases, the Vm decreases and AVm increases, and therefore PVm becomes smaller and smaller. This explains the deep in the isotherms of the most of the gases as shown in figure, that is the carbon dioxide, methane and ammonia. Actually we are saying that is when the pressure is too high, it is not too high, but it is very too high or more, that is then when the pressure is considerably high, the volume of Vm will be quite small. Now it may not be possible to ignore B, it cannot be ignored B, but that B can be considered. But as P is quite high, the pressure correction factor A divided by Vm square may become negligible is in comparison with, that is a total pressure in equation 1, which is therefore reduces to, that is a PVm minus Vm, that is this will be a negligible. Then we say that is A by Vm square, that will be a negligible. Therefore we say that is P into, that is a Vm minus B equal to, this will be a RT. R is capital here, it is small is over here. Actually this is the R capital, that is RT, or we can be P into Vm equal to RT, and this is the plus PB. Thus the PVm is now greater than, that is RT by an amount of equal to PB. As the pressure increases, the product of PB increases, and therefore PVm increases. This explains why the volume of the PVM after reaching a minimum increases with further increase in the pressure as shown in the above figure. I have already explained in the offline classes. And here also we can be explained here. It is just this is increases and particular volume it is increases. It is evident that from the above discussion that ordinary temperature, while the perfect of that is terms A divided by Vm square is predominant at low pressures, that of Pb is predominant at high pressures at some intermediate range of pressure. Therefore, the two effects balance each other. In this range of the pressure, the gas shows the ideal behavior. This explains the existence of the small horizontal portions in isotherms of the gases like carbon dioxide, methane as shown in this figure. When the temperature is high, that is I was explained that is a pressure about. Now coming to that is when the temperature is high, if a given pressure, if at a given pressure the temperature is considerably high, the volume will be becoming sufficiently large to make the volume of the A by Vm square negligible small. At high temperature, B may also be negligible in comparison to Vm, which is now sufficiently large. Under these conditions, the van der Waals equation approaches the ideal gas equation PVM equal to RT. This explains why the deviations became less at high temperature. As shown, this is the diagram. Just it is decreases, then even the pressure is increases, so that can be passes this like. This is the explain about that is a nitrogen gas. Then another one is calculation of the correction factor, that is a P. The force of attraction exerted by the single molecules which is about to strike the wall evidently depends upon the number of molecules per unit volume in the bulk of the gas. That is, it depends directly upon the density of the gas. Further, the number of molecules striking the wall at any given instant also depends directly upon the density of the gas. Thus, the total inward attraction pull on the molecules will be account as a P in proportional to the square of the density of the molecule of the gas. That is, P is directly proportional to that is the squares of the density. That is equation number 1. But again, density is nothing but density is inversely proportional to volume actually. Okay, that is mass by volume means the density is inversely proportional to volume. It is the same occupied by the gas molecules. P will be there. Therefore, we can write there is the density in the form of that is the reciprocal of volume means this equation 1 is modified, that is a P is proportional to 1 divided by V square, and here this can be proportionality constant we are removing, therefore we can write that is A divided by V square. That is the equation number 2, where A is nothing but constant and it is depends on the nature of the gas. The pressure correction factor P is also called as the internal pressure of the gas. The kinetic gas equation of the 1 mole of the can be written as P plus A divided by Vm square into Vm minus B equal to RT. That is called equation number 3. This is the van der Waals equation. The constant A and B are the known as van der Waals constant. These are the characteristics of the gas. Equation 3 is valid for 1 mole of the gas only. If there is n number of moles of the occupied, then the volume V then illustrated above the excluded volume will be given by NB, and that is compressible volume will be a V minus NB. The pressure correction factor P and N mole, that is equation number 1, will be a proportional to the N square, that is rho square. Rho is square is nothing but density square, and therefore P is that is pressure is directly proportional to that is N square for 1 mole gas. No, N square into rho square means density square. This also can be written as that will be a N square. Again, that is the density is nothing but mass by volume means the inversely proportional to volume, that is 1 divided by V square. Again, we are removing that is proportionality constant. We can write that is a into N squared, that is a V square. That will be equation number 4. Hence, the van der Waals equation for the 1 mole of the gas becomes P plus n square A divided by V square into Vm minus Nb equal to nRT. This is equation number 5. This equation number 5 is more accurate than the ideal gas equation PV is equal to nRT for expressing that is a PVT curve, that is pressure, volume and temperature curve, that is the behavior of the real gas. The unit of the van der Waals constants A and B. What are the units of the van der Waals constants? Therefore, unit of the van der Waals constant A and B are depends on the unit in which pressure and volume are expressed. It is evidence from that is equation 4 here, that the constant is expressed by that is a factor, that is a PV square by n square. Therefore, pressure into volume square divided by n is nothing but mole square. If the pressure is expressed in terms of that is a atmosphere and volume is expressed in terms of that is a dm cube, the total volume will be a that is a dm6 atmosphere per mole square, as that is a here that is a unit of that is a as regarded as B. It is the incompressible volume per mole of the gas, hence it must be a same unit volume per that is a gas dm cube per mole. And these are about that is a volume correction of the molecules. And next class I have to explain about that is the application of van der Waals equations in explaining the real gas behavior. I hope you understand. If you have any doubt, you can be asked directly through a WhatsApp or contact in a college, and you have to clarify your doubt.